Hi everyone, this is Vijayalakshmi Subnalli. Now I am going to explain the basic concepts of relations and functions for 2nd PUC Mathematics. Now, in this chapter, we will study different types of relations and functions and some basic examples of relations. Okay, before going to explain the concepts of relations and function, we will discuss the Cartesian product. Okay, if Cartesian product means there are two non-empty sets are there. Okay, let A and B. Let A and B are two non-empty sets. Non-empty sets. Then the Cartesian product. Okay, the Cartesian product of two non-empty set can be expressed A cross B. A cross B is equals to A comma B such that for every element of A which is belongs to set A and another element B which is belongs to set B. Okay, this is called the Cartesian product. Let A and B are two non-empty sets, then Cartesian product A cross B is equals to A comma B such that for every an element A which is belongs to A and the element B which is belongs to B. In this relations, okay, here we have to consider the relation. In this concept, relation, okay, let relations, already we know that, okay, what is that? The subsets of the Cartesian product is known as the relation. Here A be a non-empty set, here A be a non-empty set, then A cross A be the Cartesian product of two non-empty sets. Cartesian product of two non-empty sets. Two non-empty sets A and A. Both the sets will be A. Okay. Then relation R of A which is the subset of A cross A. The relation A which is the subset of A cross A. Okay. Now the types of relations. Okay. Here types of relations. First one, empty relations. Okay. Already we know the concepts of empty set in set theory. Empty sets means there is no element present in that set is called as empty set. Here there is no relation. Okay, there is no relation from a set A to A is called as the empty relation. Here by the definition of the empty relation. What is the definition of the empty relation? A relation R in a set. A relation R in a set A is called empty relation if no element of A is related to any element of A. No element is related to any element of A. Empty relation means a relation R in a set A is called empty relation if no element of A is related to any element of A. For example, consider one example. In your textbook, one example is there. Let A, B and set contain an elements 1, 2, 3, 4. Then relation is given by R is equals to A comma B such that A minus B is equals to 10. Let the element A and B for every element A comma B which is belongs to set A. Now we have to write the relation. Okay, A elements taken from the set A, relation can be written as, put A is equals to 1 in this equation, then the value becomes minus 9. Again, the element 2, we have to consider A is equals to 2. Put in this equation, the B value becomes minus 8. Again, for 3, B value becomes minus 7 and 4, the value becomes 6. Okay, here A is element 1, 2, 3, 4. The corresponding elements of B minus 3, minus 8, minus 7 and minus 6. Here, okay, here 1, 2, 3 and 4 which is belongs to A, but the values minus 9, minus 8, minus 7 and minus 6 are not belongs to A. Here then we say that there is no element if no element of A is related to any element of A. Here the elements of A are 1, 2, 3, 4, but minus 9, minus 8, minus 7 and minus 6 are not present in A. This is called an empty relation. Again, another one relation is universal relation. Universal relation. It is similar or opposite to that of empty relation. Okay, opposite to that of empty relation. Universal relation means a relation R in a set A is called universal relation, if each element of A is related to every element of A. Each element A should be related with every element of A is called the universal relation. Okay, a relation R in a set A is called the universal relation if each element of A is related to the element of A. Next, consider the example for the universal relation. Consider the example for the universal relation. That is, example, let A be a set of the students of boys school given by the relation R is equals to A comma B such that the difference between the heights of any two students of the school has to be less than 3 meters. Okay, let A be the set of the students of boys school. In the boys school, all of them are boys. Okay, the difference between height of any two students. Okay, we have to consider any of the two students, then their height has to be less than 3 meter. It is the universal relation because exactly no two boys have the same height. It may be or it may not. We can't say surely both are same height. Nothing. Okay. Then main concept of this chapter will be equivalence relation. Based on the equivalence relation, we have to see some examples. Before going to explain the examples, we will discuss the equivalence relation. Okay. First, the types of relations. In this, another types relations are reflexive. Okay. Reflexive, symmetric and transitive. Okay, these are the types of relation mainly. Okay, what is the definition of reflexive, symmetric and transitive? Okay, reflexive, symmetric and transitive. First definition, a relation R in a set A is called a relation R in a set A is called reflexive. Okay, reflexive if A comma A belongs to relation R for every element of A which is belongs to set A. Again, second one, symmetric. Symmetric if two elements A1 is related to A2 which is belongs to relation R, that implies A2 is also related to A1 which is also belongs to the relation R for every A1 and A2 belongs to a set A. Then the relation R is said to be transitive. Okay. If A1 is related to A2 which is belongs to the relation R and A2 is related to A3 which is belongs to R, that implies A1 comma A3 or A1 is related to A3 which is also belongs to the relation R for every A1, A2, A3 belongs to set A. These two relations are satisfied. The relation is called as the equivalence relation. Okay, that is equivalence relation. Okay, a relation R is said to be equivalence relation if it is reflexive, symmetric and transitive. Okay, what do you mean by the reflexive relation? If A comma A belongs to relation R for every A is belongs to set A, if A comma or A1 comma A2 belongs to A, then A2 comma A1 is belongs to R for every A1 and A2 belongs to non-empty set A is symmetric. For transitive, A1 is related to A2 and A2 is related to A3, that implies A1 is related to A3. Let's consider one example. Okay, for example, consider one example, that is example 1. Okay, consider an example 1. Consider one example. Let T be the set of all triangles. Set of all triangles in plane is given by the relation R T1 comma T2 such that T1 is congruent to T2. Okay, here consider the example. Here consider the example, that is T be the set of all triangles in plane. We have to consider, that is our set A becomes, here A is equals to set of all triangles. Set of all triangles in plane. Okay. Set of all triangles, but condition that relation, that is T1 is T1 comma T2 such that T1 is related to or congruent to T2. What do you mean by the congruent? Okay, the property of congruent. Congruence means all sides are equal and all angles should be equal. If we have to consider two triangles, both have the same angle and same side. Otherwise, both are replications. Okay, almost angles and edges are similar. That type of two triangles are called as a congruent triangles. First condition, what is that? Reflexive. Okay, reflexive. Okay, here R is equals to T1 comma T1. T1 is congruent to T1. We say T1 is congruent to T1. This means every triangle itself is similar, or every triangle is itself is a congruence. Hence, every triangle is itself congruent to each other. Hence, okay. Hence, R is reflex. R is reflexive for every T1 belongs to the set A. Okay, because set of all triangles, T1 is belongs to the relation A. For second one, that is symmetric condition. What do you mean by the symmetric condition? In this symmetric condition, we have to consider the true triangles. One is T1 and T2. Here relation T1 comma T2. T1 is congruent to T2. Okay. Congruence means similar. Congruence means similar. T1 is similar to T2. Again, vice versa. Okay, again, vice versa. T2 comma T1 such that T2 is also congruent to T1. That is, T1 is congruent to T2. That implies T2 is also congruent to T2. That is, T1 comma T2 is congruent to T2. That is T1 comma T2 belongs to relation R. That implies T2 comma T1 is belongs to R. For every T1 and T2 R belongs to set A, this is symmetric. It is symmetric. Then third condition, that is transitive. Now consider the relation. T1 is congruent to T2. T1 is congruent to T2 and another one triangle T3. We have to consider another one triangle T3. That is T1 is congruent to T2. Again consider T3. That is also T2 is congruent to T3. T2 is congruent to T3. T1 is similar to T2. Then T2 is similar to T3. Obviously, T1 is similar to T3. That is T1 is related T2 belongs to R and T2 is related to T3, which obviously T1 is related to T3 belongs to R for every T1, T2, T3 which is belongs to set A. Three conditions, that is T1 is congruent to T2, T2 is congruent to T3, obviously T1 is congruent to T3. Hence, it is equivalence relations. Hence, it is first transitive. It is equivalence relations. This equivalence relation, because reflexive condition is satisfied, symmetric condition will be satisfied and transitive condition will be satisfied. Based on these conditions, we will say that the example is equivalence relation. Now again consider the example number 2. That is, let L be the set of lines in plane R. Then there is a relation given by R is equals to L1 comma L2 such that L1 is perpendicular to L2. Okay, L1 is perpendicular to L2. Now check the condition for reflexive. Here A is equals to set of lines in plane R, then relation L1 L2 such that L1 is perpendicular to L2. Okay. In that, by the condition of perpendicularity, if perpendicular will be exist, if two lines are perpendicular, perpendicularity say perpendicularity not says by using only one line. Okay, if two lines are there, then perpendicular will be possibilities. Perpendicular means there is a making 90 degree. If two lines are making 90 degree, then the lines are perpendicular. For the first condition, reflexive. Okay, let relation R L1 comma L1 such that L1 is not perpendicular to L1, because if perpendicularity will be exist, must and should it contain two lines. L1 is not perpendicular to L1. It is not reflex. Again, for second condition, symmetric. By the condition of symmetric, if A1 comma A2 belongs to relation R, then A2 comma A1 is also belongs to relation R. Now, let relation R, L1 is related to L. This is line L1 and this line will be L2, such that L1 is perpendicular to L2 line. Again, L2 line is perpendicular to L1. L2 line is perpendicular to L1. That is L1 comma L2 belongs to relation R. That implies L2 comma L1 is belongs to R. Hence, or it is symmetric. Again, by the third condition, or relation transitive. Let here we have to consider the three lines. Okay, that is here line L1, L2. L1 is perpendicular to L2. Again, L2 is perpendicular to L. By the condition of transitivity, relation R, L1 comma L2. L1 is perpendicular to L2. Then L2 comma L3. L2 comma, there exists another one line L3. L2 comma L3. L2 is perpendicular to L3. But here see the image. Here L1 and L3 are parallel lines, not perpendicular lines, but L3 comma L1 such that L3 and L1 are parallel. Hence, L1 comma L2 belongs to relation R and L2 comma L3 belongs to relation R, but L3 comma L1 not belongs to the relation R. It is transitive. It is transitive. Okay. Now again discuss the third example. Now we will discuss the third example. That is show that the relation R in the set 1, 2, 3 given by the relation R is equals to 1, 1, 1, 2, 2, 2, 3, 3 and 1, 3. Here the question, show that the relation R in the set 1, 2, 3. Is not equivalence relation, is not equivalence relation. So that the relation are in the set 1, 2, 3. Now consider A is equals to 1, 2, 3 and the relation R 1, 1, 1, 2, 2, 2, 3, 3 and 1, 3. Now first condition, reflexive. What is the condition of reflexive? For every element of A, A comma A belongs to relation R, then for every A belongs to A. Here 1, 1 belongs to the relation R, again 2, 2 belongs to relation R and 3, 3 belongs to the relation R. For every element of A, 1, 1, 2, 2, 3, 3. For every 1, 2, 3 belongs to A. It is reflexive. Again, check for the condition symmetric. Here 1, 2. Here 1, 2 belongs to the relation R. That implies 2, 1 not in R. Consider the relation. 1, 2 is there but 2, 1 not present in this equation. Hence, again 1, 3 belongs to R but 3, 1 not belongs to relation R. It is not symmetric. Again, the third condition, transitive. Here 1, 2. Here 1, 2 belongs to the relation R, then and 2, 2 belongs to the relation R. That implies the third element 1, that implies 1, 2 which is belongs to the R. It is transitive. 1 is related to 2, 2 is related to 2. Again 1 is related to 2. It is transitive. But our equivalence condition is that, what is our equivalence condition? The relation is said to be equivalence relation. It is reflexive, symmetric, transitive. But the symmetric property not apply. Okay. Hence, it is not a equivalence relation. It is not a equivalence relation. Now, discuss another one example. Now, we will discuss another one example, that is we will discuss another one example. Show that R in the set Z of integer. The relation is given by R is equals to A comma B such that 2 divides A minus B. Here consider A is equals to set of integer. We already know that the integers are the numbers which contain positive numbers, negative numbers with 0. The Z contain a positive number, negative number and 0. Now here Z is equals to integer plus or minus 2 plus or minus 1 0. Okay, positive numbers, negative numbers and 0, or it can be written as minus 2, minus 1, 0, 1, 2 up to so. The relation R A comma B such that 2 divides A minus B. A and B are two positive or negative integers. Now check for first condition, reflexive. In this reflexive condition, A comma A. Okay, first relation R is equals to A comma A such that 2 divides 0, A minus A. That implies A comma A such that 2 divides A minus A will be 0. 0 is the integer. A comma A, 2 divides 0. 2 divides 0. It means it is reflexive. It is reflexive because 0 is belongs to the integer. 0 is belongs to integer. Now, second condition, symmetric. Let relation R is equals to A comma B such that 2 divides A minus, that is A comma B such that 2 divides A minus B. Again, we have to take minus outside from this, be that A minus A plus B, because the A contain positive sign and B contain negative. We will take a minus as common, then A comma B such that 2 minus of B minus A. Then that implies R is equals to 2 divides A minus B means again 2 divides minus value also, then B comma A is 2 divides B minus A. Next, it is symmetric. Again, third condition. Okay, that is transitive. Let A comma B such that 2 divides
You mesh
A
breath like I am.
minus B. Again, let R is equals to A comma B such that 2 divides A minus B, and R is equals to A comma B such that 2 divides A minus B. Similarly, R is equals to B comma C, 2 divides B minus C. Now, combine these two relations. that is R is equals to A comma B and B comma C, that is A comma C such that 2 divides A minus B plus B minus C. Hence, plus B minus will be get cancelled. A comma C is equals to 2 divides A minus C. Therefore, it is transitive. All three conditions will be obeyed. Hence, relation R is an equivalence relation. Thank you.